Rotational equilibrium is almost the same as translational equilibrium, except for rotational equilibrium, it's just things on spinning. All right. So if you have like a lever or some kind of like pivot point for an object, and it's not rotating, then you're in rotational equilibrium. And that's just the state in which the sum of all the clockwise momentums or moments equals the sum of all the counterclockwise moments about the pivot. Remember, moments is the tendency to rotate around a certain point. So, oh yeah, we've seen this before. A moment is the distance on the effort arm times the force on the effort arm. So like that would be the moment for this stuff, if we're talking about gravity, the weight of it, the distance would be from there to there, and then the force would be the weight, the force due to gravity. And then same with this, if this is balanced, then this has the same force due to gravity if this distance is the same as that distance. And this is the sigma, it's the summation symbol in math and engineering and science, because you use math everywhere, except for maybe, okay. That's just saying all of the moments are opposing and equal, so they add up to 0. That's all. That's all. Let's move on. So we're going to be talking a lot about force vectors. It's like arrows that telling which direction a force is being applied. And we have, when we talk about forces, we'll talk about scalar quantities and vector quantity, or sorry, scalar scalar quantities and vector quantities. Scalar quantities are pretty much just like numbers. It's a physical quantity that has a magnitude only, as opposed to a magnitude and a direction. So like examples would be mass, the length of something, time, volume, temperature, pressure, and speed. All of those are just without a direction necessarily. I mean, speed could have a direction, but then it would be called velocity. So scalar quantities are just, you can think of them as just amounts, like number amounts. Vector quantities are a physical quantity that has both magnitude and direction. That's what a vector is. Like from Despicable Me's. Okay. Is his name Victor? Vector? I don't know. So it's a physical quantity that has a magnitude and a direction. So if something is moving, it has mass. So that's the scalar quantity, and a direction that it's moving. That makes it a vector. So like your position, velocity, forces act in certain directions, and moments have like rotational stuff, movement. Okay, yeah. What is a force? Well, in a movie they explain some midichlorians and something silly like that. What is that? Nobody. Why did you know? So what is a force? In physics and engineering, the force, or a force, not the force. Oh my goodness, it's the pushing or pulling interaction of objects. So their vector quantities will be, and this is what I'm talking about. Vectors, drawing arrows. I think you've probably seen this before. They have a magnitude and a direction. In addition, they also have a point of application. So like there's a force acting on an object in a certain spot. And that's going to be important because forces acting in certain spots may cause a rotation or just like a translational movement, side to side or up and down. So it's important to know what the point of application is. And point of application, that's just where the vector is being applied or where the force is being applied. All right, moving on. The units of force that we'll be looking at, the British system of units, it's a pound force. We rarely use that. And then the international system of units is newtons. We've talked about that before. Newtons is a measure of force. The conversion between the two is there, but we can always do that because we got computers now, but we'll mostly be working in newtons. So yeah. Okay. Static equilibrium force principles. This is saying it's static equilibrium. If things are in static equilibrium, you always have force pair or force pairs. Forces always occur in pairs, acting on two different objects. So if two objects come into contact, there's a force from one object to the other, and then also backwards from that object to the first one. Force pairs act in opposite directions and have the same magnitude if we're in static equilibrium. So that's important. So if something is not moving, like you're standing on the ground, we talked about this already, or if there's a ball on the ground, there's the force of gravity and then the force of the ground pushing back up so that the ball doesn't move at all. Yeah, and that occurs in the x direction, the y direction, and rotationally. So if some, whoa, I don't know how much of that you heard. It doesn't matter. Doesn't matter. If something's not moving, then it's in static equilibrium, and the opposing forces have the same magnitude. Cool. When using force vectors and calculating like static equilibrium or calculating different forces upon an object, we'll definitely be using component forces, and the component forces are just a force that's made up of an x direction and a y direction. So this force has an x direction pushing it in a certain amount, and a y force in a y direction pushing it in another amount, and then it just results in this green vector. So the component forces are just the forces broken down into the x and y direction. If you have, let's do green, if you had a force that's only acting in the y direction, then it definitely has its component force in the y direction, but then its component force in the x direction has the magnitude of 0. So they always have the x and y component vectors, component forces. So as you can imagine, a resultant force is just when you're adding up the two opposing forces, or two maybe not even opposing forces. If you add two forces together, you can consider them as one force in whatever direction. So here, if you have two forces acting on an object in the same direction, then the resultant force is just adding them up, right? 7, I mean, it makes sense. And usually, I mean, we're not going to be this accurate, but usually the length of the arrow represents the magnitude of the vector. That's why this one's bigger than this one, because this has a 2 pound force. And then if they're acting in opposite directions, then, well, you subtract the 2, because this would be like a negative x direction, a negative x component, and this would be a positive. So 5 minus 2 is 3 in this direction. So it's on this object, it's like feels like it's just being pushed with 3 pound forces. That sounds weird to say. Is that it? I think that's it. I think he took his wallet. All right, goodbye.